Out there, in the huge lack of clarity of space, the James Webb Space Telescope has been investigating the smallest things for answers about the universe. This NASA's new eye above has been finding surprising pictures of stars, enormous planets, and planets. At last, something alarming has been tracked down, something so massive it could shake the real spines of all that we understand. It has specialists scratching their heads and studying whether it could ignite the farthest essential of everything. Go alongside us as we examine how the latest discoveries of the James Webb Space Telescope could pound our perception of the universe. When we explore the edge of the universe, we are examining the conspicuous universe. The recognizable universe has all the earmarks of being a window through which we can take a gander at the degree beyond the distinguishable universe. It encompasses all that we can at this point see, measure, and investigate using our telescopes and space tests. It's a variety of stars, frameworks, and terrific bodies within our grasp of seeing. By and by, the noticeable universe is just a little piece of the entire universe. Envision it as a slice from a colossal pie that we're ready to study and handle, while the total size and condition of the universe at large remain a mystery. Scientists estimate the width of our perceivable air pocket to be around 93 billion light-years. A light-year estimates the distance that light, the fastest thing known to mankind, goes in 1 year, around 5.88 trillion miles or 9.46 trillion kilometers. So when we talk about the expansiveness of the distinguishable universe being 93 billion light-years, we are examining a huge stretch. Around 13.8 billion years ago, the universe burst into existence in an unbelievably strong impact. This event started what we call the Big Bang. Since that tremendous birth, the universe hasn't simply been developing. It's been progressing rapidly in its improvement. Confounding powers, like the bizarre dark energy, have shown up to be driving the speed increase, expanding the limits of the universe further apart. As the universe stretched out, matter began to group together, affected by gravity. This gravitational force joined particles, birthing stunning plans, stars, colossal frameworks, and eventually planets like our own Earth. Picture the universe passing by as these colossal structures outlined, forming into the exceptional yet persistently developing eccentricities we see across the universe today. No matter its huge size, the universe is stunningly void. On the off chance that we somehow end up pulling back our entire planetary gathering to the size of a quarter, the nearest star would still be about the length of 2 soccer fields away. This infinite quality expands right inside our own Milky Way galaxy, which is only one among billions in the noticeable universe, giving us a sense of the sheer size of boundless space. Now, you could ask, why can't we simply see all that exists in the universe? There are a couple of reasons for this limitation. Primarily light, the fastest thing known to man, still takes time to go through space. This means that when we look at faraway objects, we are basically focusing on the past. The farther an object is, the more time its light has taken to reach us. It's like looking through a tremendous time machine, unrolling the history of our universe as we observe systems millions or even billions of light-years away. The real universe is expanding. Imagine spots on the outer layer of a developing inflatable. As the inflatable enlarges, the spots move farther apart. This same rule applies to the universe. Galaxies, like those spots, are drifting apart as the surface of space expands. This expansion causes the light from faraway objects to go through a shift known as redshift. Essentially, the frequencies of light stretch as the objects move away, advancing toward longer frequencies and often appearing to be ruddy in color. Given these factors, light's development time, the expansion of space, and the universe's constant development, it's not out of the ordinary that we haven't yet completely seen all that the universe offers. Even with our particularly advanced telescopes and technology, our view is still bound by these basic properties of the universe. The journey to grasp the possible edge or limits of the universe has captivated the minds of vast people across disciplines. While indisputable answers remain elusive, 3 recognizable hypotheses have emerged, each offering fascinating perspectives on the development of boundless space. The first speculation suggests that the universe grows tremendously, going on interminably without a recognizable edge. This idea lines up with the cosmological principle, which states the isotropy of the universe, that it seems reliable from any vantage point. Assuming the principle holds, it suggests that the universe lacks a cutoff and grows boundlessly toward every path. The second speculation offers an alternative view, proposing that while the universe may indeed be limited, it lacks a clear edge. Instead, it could look like an enormous circle or a twisted space, like Earth. In this situation, if one were to travel endlessly in any direction, they would ultimately return to their starting point, like circumnavigating Earth. The third speculation, the multiverse hypothesis, presents an intriguing thought that our universe is only one of innumerable others. Imagine a limitless number of parallel universes, each existing with its own set of physical laws, constants, and properties. These universes may be completely different from one another, working independently, or they may be interconnected through complex systems, forming an immense and perplexing multiverse. The James Webb Space Telescope, JWST, stands as a seal of potential, enlightening the mysteries that lie at the gigantic starting points of the universe. This mind-boggling instrument has an unrivaled capacity to unravel the befuddling past of our universe, allowing us to peer a long way beyond what was previously possible. The JWST is a mechanical marvel, designed specifically to observe the universe with astounding precision. Its high-level capabilities stretch our vision to the earliest moments of the universe. In fact, a critical study published in the renowned journal Nature revealed the JWST's discovery of 6 gigantic galaxies dating back between 500 million and 700 million years after the Big Bang. Incredibly, these ancient worlds are far bigger than expected for their early presence, testing the prevailing hypotheses of universe development. In addition, their advancement in the early universe is genuinely astounding. What's uncommon about these revelations is the level of intricacy in these antiquated frameworks. This goes against the presumption that cosmic systems structure gradually over time. These tremendous universes show a level of complexity practically identical to our 13-billion-year-old Milky Way universe. The sheer number of stars inside these titanic behemoths surpasses our assumptions, with every universe boasting a complete mass a few times more prominent than our Sun. Strikingly, one of these universes may even have a mass up to several times that of our Sun, obscuring the already titanic size of our Milky Way. The JWST's unmatched capacity to investigate the universe's secret spaces depends on its utilization of infrared light, an undetectable range to the unaided eye. This amazing power enables the telescope to catch the weak discharges from antiquated stars and cosmic systems, revealing enormous leftovers that have endured for billions of years. Essentially, the JWST acts as a time machine, moving our vision back through the ages and offering an enthralling look into the universe as it appeared roughly 13.5 billion years ago. The continuous discovery of gigantic cosmic systems, tensely nicknamed universe breakers, has changed our understanding. It's like changing history, a stunning twist that challenges many of the models we had spread out for early universes. Initially, we believed cosmic systems formed from humble beginnings, starting as small assortments of stars and dust. They were thought to advance steadily over time, expanding in size and intricacy. However, the universe breakers have shattered these ideas. When the JWST's data and its high-resolution pictures uncovered these colossal structures, these enormous behemoths appeared seemingly out of nowhere, as if they had just been found. Astonishingly, our past understanding of astronomical development has been called into question. Digging further, analysts utilized spectroscopic techniques to analyze light across various frequencies. This investigation holds the key to unlocking crucial insights about these puzzling systems, such as their structure, size, and distance from Earth. It's like a tremendous analytical story, with light as the key to uncovering the mysteries of these gigantic entities. The astounding discoveries from the James Webb Space Telescope have changed our understanding of the universe to unprecedented levels. This cutting-edge telescope, operated by a global team of space scientists, has recently revealed a shocking discovery: the identification of the oldest and most distant systems ever observed. These universes transport us back to when the universe was just a small part of its ongoing age, existing only a brief time after the Big Bang. The James Webb Space Telescope, out in the vast darkness of space, has been searching for answers about the universe. It's NASA's latest powerful instrument, capturing staggering pictures of stars, systems, and planets. Recently, it made a discovery so unimaginable that it could change how we understand the very fabric of the universe, leaving experts confounded and curious about its true potential implications. When we study the universe, we begin with the visible universe, a window into the vastness beyond. This apparent universe includes all that we can currently relate to our telescopes and space probes, including stars, galaxies, and other celestial bodies. However, it's just a tiny piece of the entire universe. Scientists estimate the width of our perceptible universe to be around 93 billion light-years. A light-year measures the distance light travels in 1 year, about 588 trillion miles, making the range nearly infinite. Around 13.8 billion years ago, the universe began with the Big Bang, a massive explosion that triggered the incredible expansion. Since then, the universe has been evolving and accelerating, driven by mysterious forces like dark energy. Matter began to blend under gravity, forming stars, worlds, and eventually planets like Earth. This constant process shapes the universe's vast size, allowing us to observe only a small part of its infinite complexity. Even with progress, much of the universe remains dark and empty. Despite how far we've come in exploring space, the majority remains hidden. Even with the power of the James Webb Space Telescope, vast portions of the universe remain out of reach. However, its discoveries continue to reshape our perception, offering a brief glimpse into the incredible wonders that lie just beyond our sight. The vastness of space continues to astound and move us. With every earth-shattering revelation, we are slowly piecing together a more complex understanding of the universe's history and future. The James Webb Space Telescope is a tool that could forever change the way we think about space, time, and the very nature of our reality. The implications of the JWST's revelations extend beyond novel observations. They challenge the very foundations of current cosmology. If these massive universes existed so early in the universe's history, it compels us to rethink current models of galaxy development. For years, researchers have adhered to the idea that galaxies grow slowly, starting as small, dense clusters of gas and dust, gradually evolving over billions of years. The discovery of these gigantic worlds, formed in the first few 100 million years after the Big Bang, presents a mystery that doesn't align with this slow evolution. This discovery opens up new questions about the nature of galaxy formation itself. How did such enormous, complex galaxies form so quickly after the universe's inception? What forces were at work during those early eras that enabled rapid star formation and the development of galaxies on a large scale? These questions not only challenge our current understanding of the early universe, but they also push the boundaries of our knowledge of physics, particularly concerning the behavior of dark matter and dark energy during the universe's earliest stages.